Thank you for attending to my talk. I will present two recent results we have obtained on two different physical situations. The first of which is related to the generation of very fast jets produced by the implosion of cavities such as this bursting bubble that you can see here. This phenomenon that takes place at every moment in the ocean produce very tiny drops that are ejected into the atmosphere, and please notice that bubbles with diameters of the order of 5 micron can produce drops with velocities exceeding 100 meters per second with diameters below 100 nanometers. And once these drops evaporate, they generate nucleation sites for water to condensate, form either clouds, water clouds, or ice crystals. So this phenomenon has many other technological implications, as I will explain later on. And this particular problem, I will explain the general ideas through this particular problem, has been analyzed using, firstly, numerical simulations using Arias, which shows that, well, in these numerical simulations we have varied the honest organ number, which is the inverse of a Reynolds number based on the capillary velocity, by a factor of 10, which means in dimensional units, fixing the diameter of the drop by means that we have varied the viscosity by a factor of 10. Then what we can see from the numerical simulations is that the initial spherical bubble is deformed into a truncated cone, and from the base of the truncated cone, with this opening angle beta, which is for this particular case of the order of 40 degrees, a very fast jet is ejected. This physical situation has been traditionally analyzed using the theory presented over 2 decades ago by Seff et al. In this Nature paper. And this theory states that these jets are ejected due to a balance between a capillary pressure and the dynamic pressure in the liquid, such that this balance holds for a finite time during the jet evolution. If this was true, then the Weber number defined as a ratio of these two pressures should remain constant in time. Very recently, Lai, Eggers, and Deike have made use of this classical theory, in which the authors state that the jet shapes are self-similar, with distances evolving in time as tau to the 2/3, because this balance implies that distances vary in time as 2 to the 2/3 and velocities as tau to minus 1/3, with tau the dimensionless time to the ejection of the jet. They claim that, in fact, the theory of Seff et al. Is applicable to explain the generation of bubble bursting jets. But this implies these must remain constant in time. And what happens if we analyze our numerical results? If we analyze our numerical results, what we obtain is that this is constant value of the Weber number. What we observe from the numerical results is that the Weber number is always very large, which means that capillary pressure is always much smaller than the dynamic pressure. So this cannot be the reason for the ejection of these jets. And moreover, the local Weber number varies in time as tau minus 1/2. So another theoretical framework needs to be stated in order to explain the emergence of these very fast jets. And so what we propose is to divide the jet ejection process for this physical situation and in general situations as a two-stage process. The first one is what we call the acceleration stage, in which the pressure differences between the air pressure and between the liquid pressure at the side of the interface and far from the interface, this pressure difference accelerates the liquid inwards with the capillary, with the characteristic velocity estimated by simply the order of magnitude by the Euler-Bernoulli equation. And what we find is during this acceleration stage, the liquid is accelerated inwards towards the axis of symmetry, and once this acceleration stage has finished, this acceleration stage fixes the value of the flow rate per unit length far from the axis, as well as the shape of the interface right before the jet is ejected, because here the shape is really very important. Why Q infinity is so important here? Because during the second stage, the jet ejection stage, you can see here the ejection of the jet at 3 different instants of time. You can see here the velocity vectors at these 3 very different instants of time, and these velocity vectors have not changed at all. So the process is so fast, and the radial inertia of the liquid is so large that this Q infinity remains constant. And so the paradigm changes by saying that these jets are formed by simply stating that the flow rate per unit length far from the axis remains constant in time. And this radial flow rate, what does is to force the radial collapse of the cavity walls, and then this is the reason for the generation of the jet. So capillarity does not enter into this physical description at all, except for fixing Q infinity at the beginning. Just to give some numbers, this characteristic velocity for the case of a 5 micron bubble, the radial velocity is of the order of 1 meter per second, but the jet velocity is 300 meters per second. I mean that you multiply by a factor of 100 the velocity of the jet with respect to the radial velocities, and therefore the dynamic pressures by a factor of 10 to the 4. And just to check whether the jets generated by bursting bubbles are generated by this mechanism, we performed different types of simulations that were originally performed by Dieter and Fabian Reuter, imposing the radial velocity at a certain distance, which means that we fix the value of Q infinity and provide with the semi-angle of a cone. We carry out these numerical simulations, find out that this problem possesses a self-similar solution, which is a self-similar solution in which distances varies in time as tau to the 1/2 and velocities as tau minus 1/2, such that the product of these two remains constant in time, which is the boundary condition we impose at infinity. We solve this numerical problem for different opening semi-angles, okay, and then find which is the self-similar shape of the jet for each opening semi-angle of the cone. Then here we have the time evolution of the jet shapes for the case of bubble bursting jets, and if we rescale all these shapes with distances as tau to the 1/2, what we can see is that all of them collapse onto the self-similar shape that we have found through this other type of numerical simulation. So, I mean, it is a self-similar solution, but not of inertial capillary type. So, these jets are purely inertial in nature. So, of course, this physical phenomena is present in many other, this physical mechanism is present in many other physical phenomena, and so we want to generalize it to whatever initial shape we have after the acceleration stage, okay? So not only a cone, but a parabola or other shape by fixing Q infinity. And this theory we have developed is applicable to the case of slender cavities, okay? Then, so this is the picture that we want to solve now, because we want to generalize this physical mechanism to other physical situations by we just fix Q infinity and the initial shape of the cavity. And our purpose is to determine the width of the jet, the time evolution of the width of the jet, the velocity of the jet at the base of the jet, and the vertical position of the jet. With these three time-varying functions, you can perfectly find out which is the spatiotemporal evolution of the velocity field and also the shape of the jet, because the local Weber number is very large, and therefore these equations are ballistic. So the velocity of this material point is conserved in time. And so by applying continuity and the fact that the velocity is conserved, if you have these three functions, you have everything. So in order to find these three functions, what we first do is that this is a very fast process, a vorticity is not produced, and therefore what we do is to solve the Laplace equation subjected to the boundary condition that Q infinity is given, and also this is a slender configuration, so the interface is located here, okay? this region here is the axis of symmetry, so the interface has disappeared here, so here we have no flow, and we have to solve Laplace equation with this boundary condition, and which is the boundary condition here. Okay, the process is so fast that the Euler-Bernoulli equation simplifies to partial phi with respect to time equals 0. So the boundary condition is that phi here, the potential velocity is 0, meaning that the velocity is perpendicular to the interface, okay? So all we have to do is to solve this subjected to these boundary conditions, and this is the first step to find these three functions. How do we solve the Laplace equation in this configuration? By a superposition of sinks located at the axis of symmetry, only of course where the free interface is located, because here we would have a singularity, and as you can see here, if this is the magnitude of Q infinity, the, the flow rate per unit length of these sinks here is larger because you have no flow here, and therefore your unknown is this delta Q, which is a function of seed and time. How do you find this delta Q, which is the excess of the flow rate intensity of the sinks with respect to Q infinity? By simply imposing that the tangential velocity, the velocity along seed at the interface is 0, because there the potential is 0. And this provides you with this integral equation that you can solve very easily, and then solving this, you obtain the universal solution for delta Q. Once you have delta Q of C and T, what you do is to make use of the kinematic boundary condition, because since you know the initial shape of the cavity, you know the radial velocity, you know the instant when a point at the free interface will reach the axis of symmetry. Then you know this delta Q, and therefore, since what we do is for several, we parameterize the initial shapes of the cavities through this exponent. So the exponent n equal 2 is a cone, n equal 4 is a parabola, etc., etc. So different shapes, n means different shapes, and we solve this integral equation by simply taking solutions of this type, introducing this into this, and because delta Q, I insist, we already know. We can see what's the shape of delta Q later, and we can get this explicit solution for Cz with this prefactor that can be exactly calculated, and with this dependence of time as 1 over n. For the case of cones, we have tau to the 1/2. For the case of parabolas, tau to the 1/4, etc., etc., with the prefactor exactly calculated. Now, we already have Cz. What happens with the velocity of the jet? Okay, what we do is to simply use the Euler-Bernoulli equation in the moving frame of reference, okay, in this region near the base of the jet, okay, and since we are moving in the moving frame of reference at the velocity dc jet d tau, so the Euler-Bernoulli equation in this region, in this thin region of the order of r jet is quasi-steady, and then P pressure plus 1/2 the velocity of the moving frame of reference squared remains constant. Here we have the maximum pressure, okay, which is the pressure of the gas plus 1/2 of dc jet d tau squared, and then this is, since the pressure here is also the pressure of the gas, then the velocity in the moving frame of reference of the liquid is also dc jet d tau. And then in the laboratory frame of reference, the velocity of the liquid in the jet is twice dc jet d tau. Since we have c jet, we can explicitly calculate which is v jet. For the case of cones here, what you can see is that these jets are more violent than those produced after the impact of a drop on a solid wall. For the case of a cone, you have dependence of the type tau to the 1/2. For the case of parabolas, you have dependencies of the c jet of tau to the 1/4, and therefore the velocity is tau to minus 3/4. So this is faster than, for instance, the splashing of a drop on a free interface, because this is the same as a Wagner problem, but in an axisymmetric geometry. So And now it only remains to find which is the equation for Rjet. And we have to recall that the zinc distribution that we have found, this is delta Q, the zinc distribution at the axis of symmetry is Q infinity plus times 1 plus delta Q. This zinc distribution exactly balances the flow rate that we have imposed far from the axis of symmetry. But the Euler-Bernoulli equation at the scale of the base of the jet tells us that you have to retain, in this inner region, you have to retain the dynamic pressure. And the term 1/2 of dc d tau squared. And this region here is a streamline, meaning that in this region here of length, Rjet, characteristically Rjet, what we have is that the normal velocities are 0, and therefore the flux, the volume flux through this part of the interface is 0. Then the suction of the the sinks located in this region cannot suck the flow rate that is imposed far from the interface, because along this region you cannot. So the interface is not shrinked radially, because in the moving frame of reference the normal velocity here is 0. And then the equation that fixes Rjet is simply the one that states that mass conservation enforces the generation of a jet such that it compensates the flow rate that is not suctioned by this part of the interface, because the things located here cannot shrink radially the interface. And so what we have here is that this is the this is the flow rate that would associated with the sinks located here, okay? Since in the moving frame of reference this cannot be absorbed by this sink distribution, then a jet is formed, since we already know which is the velocity, which is twice dc jet d tau. We simply solve this equation, because we know delta Q, that for at the base of the jet is like 0.7, and then we find with this equation, because we already know delta Q, with this equation that permits you to calculate which is Rjet as a function of Cjet. And in order to test our ideas, then we take these equations we have derived, and in the green line you can see which is our prediction for the local Weber number when compared with the numerical simulations carried out for different values of the Weber number. And we can see here also the radius of the jet, the product of Rjet, dc jet, d tau, and the velocity of the jet, which has initially is like 200, 300 times the capillary velocity, okay? And initially the radius of the jet is like less than 1% of the initial radius of the bubble. As you can see that the velocities are much in the jet are much larger than the characteristic radial velocities that drive the implosion of the cavity. This is for the case of conical cavities. What happens if the shape of the cavity instead of a cone is a parabola? This is what we have in this physical situation, in this recent publication with also with Dietering PRL, that here the jets are produced by the implosion of a cavitation bubble, which is produced after a former cavitation bubble is produced and deformed into a torus. Once this torus implodes, then it generates a shock wave that forces the implosion of this, the neck of this second cavitation bubble, which locally is, as you can see here, a parabola. And then let's see if our theory is able to reproduce the velocities that we can find here, which exceed 1,000 meters per second. What we find here is experiments red dots in the full line is the numerical results, and this dotted line is the theory before the jet is ejected. So this is a acceleration stage, and this is a comparison between the predictions during the jet ejection stage. Once the jet is ejected, the product of R jet, DC jet, d tau is constant as predicted, that C jet goes like tau to the 1/4, etc. And this last slide shows that the total analogy between this physical phenomena and this other, in which a cavity is formed, a work done with the Barrage, Van der Meer, and Stefan Gekle. Once a solid impact free interface, it entraps a large bubble, which locally is a parabola. And as you can see here, the experiments by Gekle and those by Fan and Bussmann, you can see that both of them, for the case of parabolic cavities, can be very well produced by reproduced by this theory. And more details can be found in this recent publication. And the other problem I will talk about is this one, that I think that has been treated the week before, which is we have analyzed which are the conditions under which a drop falling on a substrate can skate over a thin gas or vapor layer. This is a relevant phenomena, for instance, for heat transfer applications, because when you want to cool down a solid, what you want to do is to contact the solid with a very cold liquid so that it cools down quickly. But what happens? What happens is that under some circumstances, the liquid evaporates, and then there exists a stable vapor layer that separates the liquid from the wall. Since the heat conductivity of the gas is so small, then the heat flux is very much reduced. And so the main question here is to control these processes, and also other ones, like under which conditions an impacting drop will rebound, other type of phenomena. It's important to know which is the minimum gas or vapor film thickness that separates the liquid from the wall, and this is what we will try to analyze here. So we first do a revision of the literature. So we start with Dushman and Joseran, who is here, and what we see from their numerical simulations is that a drop falling on a wall entraps a bubble whose characteristic thickness at the axis of symmetry is proportional to the radius of the droplet times the Stokes number 2 minus 2/3. This Stokes number is a Reynolds number with, defined with the density of the liquid and the viscosity of the gas, okay? But the minimum field thickness is not reached here, but here, at an off-center position. So this is very well characterized. So the point is what happens here, which is this HM. What did Christophe and Logan found? What they found in their numerical simulations is that this minimum film thickness depends as is proportional to Weber minus 1/3 Stokes minus 10^9, okay? 1 year later, Mandre and Brenner published this paper where they performed simplified numerical simulations and also developed a theory which states that the minimum film thickness has two expressions depending on whether you can neglect or not the capillary pressure. If you cannot neglect the capillary pressure, you have this expression here. If you can neglect the capillary pressure, you have this other expression, but neither of them coincide with the expressions found by Joseran and Dushman. More recently, Chantelot and Losse published 2 papers in JFM where they let drops fall on a heated substrate and measure this minimum film thickness. And they claim that in the case the substrate is not superheated, their experimental results are well reproduced by the theory of Mandre and Brenner, and what they do for the case in which the substrate is superheated is to apply Mandre and Brenner theory and deduce this expression for the minimum film thickness, which of course depends on the vapor production in the region in which the minimum film thickness is attained. So the problem is that we did not believe in the theory of Mandre and Brenner and Chantelot and Losse, and we published this paper, which simply makes use of a very simple physical idea. The minimum film thickness is attained at the region where the maximum pressure is attained. And in this region, what you need to make sure is that gas pressures are sufficiently large so that to compensate the liquid pressures. Okay? And this region is so thin, of the order of 100 nanometers, that in the gas you can use lubrication. So how do we know all these things were? So for Madeleine and Sasha, and it's very easy to know where you find the maximum pressure. Using Wagner theory, you know that this is located at a radius, a square root of 3 times the dimensionless time. There is where you find the maximum pressure. And you can also, this potential flow theory can also predict which is the tangential velocity in the liquid where the maximum pressure is attained. You can also predict which is the maximum pressure at this off-centered position, and you can also predict which is the width of the region where liquid pressure variations of the order of delta PM take place. Okay? So we can predict all this. What happens? That there are situations in which the width along which the pressure variations in the gas take place is not given by the length in which the liquid pressure variations take place. This happens when the capillary pressure is able to compensate the maximum pressure. And so when we balance the capillary pressure with the maximum pressure, we find which is the width of the region where gas pressure variations takes place in the case of capillary effects take place. So we will deduce 2 expressions depending on whether we take for the gradient of pressures this length or this length. When the criterion is that when this length LC is smaller than HAM, then the length is HAM, and otherwise it's LC. We do this, and then what we do is to apply the classical lubrication mechanism. So we have the tangential velocity, we have the maximum pressure, so we have the pressure gradient. So all we have to say is that in this slightly converging region, so the Couette flow is balanced by the Poiseuille flow induced by the pressure gradients, and this provides you with, since you know VM, the length HAM or LC, you know everything, then you obtain this for the case of the capillary regime. So you find Duchman and Josserand, and for the inertial regime, you find this expression, neither of which are similar to those deduced by Mandre and Brenner. So we did, to know which of the 2 expressions is correct, so we did numerical simulations in this paper, which was published recently, and we compare the Mandre and Brenner and Chantelot and Losse, or our own expressions in full symbols and open symbols, the Mandre and Brenner and Chantelot and Losse. Here, this is the capillary scaling, and for the inertial scaling, which is valid for large values of the Weber number, you can see that the deviations in our case are much smaller. We can also predict with our theory the velocity profiles in the region where the maximum pressure is attained. You can see here in full lines the velocity profiles and the numerical results. And finally, we can also explain the lift-off instability, which was published 10 years ago by Kolinsky, Mahadevan, and Rubinstein, where they find that when a drop impact unescapes over a gas layer, what happens is that this distance here increases in time. And so the point is how this increases in time. They reported that it increases in time, but why and how? So we, since you apply exactly the same lubrication equation in the region of maximum pressure, because the rate of volume change in this 2D problem is negligible when compared to the co-ed flow. This is negligible, and then all you have to do is to use mass conservation in this thin flow. You can even use the same idea in the case you have a vapor production. And so here Hn is depends on time parametrically, and you obtain these expressions which depends on Weber, Stokes, and time, and we have compared them with our numerical results, and so we think we have also explained this phenomenon that had not been explained before. And thank you very much for your patience and your attention.
We are out of time, but there are still any questions. I believe some of you, at least some of you, have questions to be asked, but you can do this during the drink reception, which is in few minutes. But however, if you want to say something about this presentation, please do this. No? No. Okay, thank you very much, Jose.